On the basis of the commutation relations, Dirac, in his 1926 paper in Proceedings of the Royal Society of London, had already pointed out that one cannot answer any question on the quantum theory which refers to numerical values for both the p and q. Pascal Jordan expressed it thus: for a given value of q, all values of p are equally possible. In a letter to Pauli in October 1926, Heisenberg observed that it is meaningless to speak of the place of a particle with a definite velocity. Encouraged by Pauli, he wrote up a comprehensive manuscript which was submitted to the Zeitschrift für Physik at the end of March 1927. The English translation is entitled Quantum Mechanics and Measurement. Assuming a Gaussian distribution of measurement errors in the position q, Heisenberg expressed the squared probability amplitude in this form, and for the probability amplitude itself, the form here. The momentum distribution is related to this by S of p equals integral from minus infinity to infinity S of q times S of q and p dq, where S of q and p is the joint probability given by e to the power I pq by h cross. But e to the power I p dash q dash by h cross is itself another constant, and so this expression simplifies to this form here. And then upon performing the integration, we get this expression here. Comparing this with the distribution of measurement errors in the momentum p, Heisenberg concluded that the product of the uncertainties is delta q times delta p equals h cross. In 1929, Robertson showed that the uncertainty principle can be generalized for any two Hermitian operators A and B in terms of the expectation values of their fluctuations delta A and delta B and that of their commutator, so that the expectation value of delta A times the expectation value of delta B is greater than or equal to half times the modulus of the expectation value of I times the commutator of A and B. For the case A equals momentum p and B equals position q, this reduces to delta q delta p is greater than or equal to half h cross. Ditchburn pointed out in 1930 that according to the general theory of errors, the fluctuations and the errors in the position and momentum are related by these expressions, and he proved that the limiting condition of equality in this expression is obtained for a Gaussian error distribution, thereby reconciling this expression with the one Heisenberg obtained. In 1923, Heisenberg was defending his PhD thesis at the University of Munich. One of his examiners was Wilhelm Wien, and one of the questions he asked at the oral examination was about the resolving power of microscopes. Heisenberg was unable to answer this question, but he was apparently conscientious enough to study it after the examination. This diligence served him well 4 years later when he was seeking the physical basis for the reciprocal limitation between the precisions of measurements of p and q. He asked himself whether it is not possible by a more profound analysis of the kinematical and mechanical conceptions to obtain an intuitive understanding of the quantum mechanical relationships. To determine the position q of an electron, one has to illuminate it with radiation and observe it under a microscope. But due to the Compton effect, the impact of the light quantum upon the electron changes the electron's momentum. This change being greater the smaller the wavelength of the light used, that is, the more accurately the position is determined. Bohr pointed out that the reason the change in momentum of the electron cannot be sharply determined is because the direction of the scattered photon cannot be determined within the bundle of rays entering the aperture of the microscope. Likewise, Heisenberg showed that the precision in the measurement of energy is smaller or the energy uncertainty is greater, the shorter the time interval of the measurement, delta E delta t approximately equal to Planck's constant. Note, however, that time in quantum mechanics is not a dynamical variable and is not associated with an operator, so there is no commutation relation involved here. These considerations led Heisenberg to declare all the concepts that are used in the classical theory for the description of a mechanical system can also be defined for atomic processes, but the experiments which lead to such definitions carry with them an uncertainty if they involve the simultaneous determination of two canonically conjugate quantities. He further made the provocative statement, the trajectory comes into existence only when we observe it. This statement reflects the strong influence of the philosophy of logical positivism upon Heisenberg and many others of that time. At the end of his paper, Heisenberg concluded, in view of the intimate connection between the statistical character of the quantum theory and the imprecision of all perception, it may be suggested that behind the statistical universe of perception, there lies hidden a real world ruled by causality. Such speculation seems to us, and we stress this with emphasis, useless and meaningless, for physics has to confine itself to the formal description of the relations among perceptions. We see here one of the earliest statements of the Copenhagen philosophy. The philosophical implications of Heisenberg's paper were not immediately recognized, but they certainly were by the time of publication of Wolfgang Pauli's hugely influential encyclopedia article in the Handbuch der Physik, published by Springer in 1933, wherein Pauli began his exposition of the general principles of quantum theory with the statement of the uncertainty relations. This approach was also followed by several classic textbooks on quantum mechanics in subsequent decades, including those by Schiff in 1949, David Bohm in 1951, and Landau and Lifshitz in 1958. Let us now turn to the other major pillar of the Copenhagen interpretation, namely Bohr's concept of complementarity, which originated from his final acceptance of wave-particle duality. Bohr's first public exposition of this concept was at the Istituto Carducci in Como on 16 September 1927 at an International Physics Congress commemorating Alessandro Volta's 100th death anniversary. I was fortunate to spend a week at a conference at this lovely Italian lakeside town in the 90s. The September 1927 meeting was attended by a who's who of stalwarts such as Max Born, Satyen Bose, Louis de Broglie, Leon Brouin, Arthur Holly Compton, Peter Debye, William Duane, Enrico Fermi, James Franck, Jakob Frankel, Walther Gerlach, Edwin Hall, Werner Heisenberg, Hans Kramers, Max von Laue, Hendrik Anton Lorentz, Robert Millikan, John von Neumann, Friedrich Paschen, Wolfgang Pauli, Max Planck, Meghnad Saha, Adolf Schmeckal, Arnold Sommerfeld, Otto Stern, Richard Tolman, Eugene Wigner, and Peter Zeeman. We have the relations E equals h nu and P equals h cross k. The quantities E, energy, and P, momentum, are particle concepts, whereas the quantities nu, frequency, and K, the wave vector, are wave concepts. The particle concepts are necessary for explaining phenomena like the photoelectric effect and the Compton effect, whereas the wave concepts are necessary for explaining interference and diffraction. At this meeting, Bohr said, on the one hand, the definition of the state of a physical system as ordinarily understood claims the elimination of all external disturbances. But in that case, according to the quantum postulate, any observation will be impossible, and above all, the concepts of space and time lose their immediate sense. On the other hand, if in order to make observation possible, we permit certain interactions with suitable agents of measurement not belonging to the system, an unambiguous definition of the state of the system is naturally no longer possible, and there can be no question of causality in the ordinary sense of the word. The very nature of the quantum system thus forces us to regard the space-time coordination and the claim of causality, the union of which characterizes the classical theories, as complementary but exclusive features of the description, symbolizing the idealization of observation and description respectively. In other words, the prediction or retrodiction is possible only if a system is closed, that is, unaffected by external disturbances. For an open system, strictly speaking, no state can be defined. But in the quantum domain, any observation of the system implies a disturbance. The system, if observed, is always an open system, and the space-time description presupposes observation. So why is simultaneous use of complementary descriptions possible in classical physics? This is only because of the extremely small value of the quantum of action as compared to the actions involved in ordinary sense perceptions. In his Como lecture, Bohr did not explicitly define complementarity, and when he did, he was often notoriously incomprehensible. The first to give a precise definition was Wolfgang Pauli in his article for Handbuch der Physik. Pauli called two classical concepts complementary if the applicability of the one stands in relation of exclusion to that of the other, for example, position and momentum, in the sense that any experimental setup for measuring the one interferes destructively with any experimental setup for measuring the other. Note that Pauli ascribed complementarity to two concepts which belong to the same classical mode of description, such as the particle picture in the case of position and momentum, and not to two mutually exclusive descriptions a la Bohr. Wigner remarked after the Como Congress that Bohr's lecture will not induce any of us to change his opinion about quantum mechanics. For Neumann observed, well, there are many things which do not commute, and you can easily find three operators which do not commute. But this very vagueness and the resulting conceptual flexibility of the Copenhagen interpretation may have enabled it to survive. According to Feuerabend, one of the reasons for the persistence of the creed of complementarity in the face of decisive objections is to be found in the vagueness of the main principles of this creed. And that's as good a place to stop as any. See you next week.